There we go. All right. Let me start over again. Today is this webinar kicks off the next 3 weeks of our interaction, where we'll be telling you about YouthAstroNet, the activities you can do. You'll learn how to use MicroObservatory, learn how to navigate our online portal for activity. We kind of want to get you started personally, but a lot of our interaction over the next couple weeks will be self-paced, where you'll get on the portal, you'll try things out, you'll post questions and post images that you create onto the forum. You probably want to plan to spend about 8 to 10 hours over the next 3 weeks doing that. You can spend lots more. There's lots more to do, but the second webinar will have a series like there were for today and tomorrow to choose from on Monday the 25th and 26th. And then next week, we actually have a series of optional office hours where we'll be on the Zoom, and if you have a question and you really want a personal live answer, you can just click into the Zoom, but you don't have to. It's just an opportunity. So today, you are the learners. We'll turn our attention to what your students will do next week, but this first week we want you to learn a little bit about telescopes, a little bit about astronomy, kind of start asking questions. As you know, the centerpiece of YouthAstroNet is our robotic telescope network called MicroObservatory. And we have a network, we have 5 telescopes that may be online. Typically 3 to 4 are online at any given time, and they have names. They're named, I think we discussed this in the informational webinar, they're named after famous astronomers, Annie, Ben, Cecilia, Donald, and Ed. And there's material on the online infrastructure to find out who those people are that these telescopes are named after. Right now, there are 2 telescopes in our Arizona observatory location, and 1 up on our roof. Ben is actually on the roof, and this is a picture of Frank with some students from Adrian's after-school programs. Actually, I can, oh look, I'm going to bring, this is a live view of the telescope on our roof, and it apparently is taking a picture at the moment. It's you can see that it's moving slowly. I think you can see that. You can also see that we had some snow yesterday. It's cold here, but this is how these robotic telescopes work. There's no human in the loop. You control them, and I'm going to show you how you control them. I'm going to pull that little webcam out of the way. We actually have a webcam of the ones in Arizona. You can see it's bright and sunny there, but the telescopes are not pointing up at the moment. Okay. So I'm gonna, let's see, escape out of the slideshow and try and, so the online portal, unfortunately doesn't have a very memorable URL yet. We don't have YouthAstroNet.org yet, but it is up here in the corner, and Erica will send you that URL along with a username and a password, a temporary password to log in no later than the end of tomorrow. So it's WAPS. I think of it as we are people of science. We are people of STEM. waps.cfa.harvard.edu/eduportal, but Erica will send you that. So when you get to that web page, you can see that there's series of courses. We're using a course management system for the YouthAstroNet infrastructure. It's open source. It's called Moodle. But if you click on the YouthAstroNet page, you'll see that there are 3 portals. Actually, I see 3. When you get your password, you'll only see 2. We aren't opening our parent portal yet. We still have some work, and you guys are going to help us know the kinds of resources for parents. And your students would only see 1 portal. So this YouthAstroNet activity portal is the main one for using the telescopes for pursuing activities. This Educator Portal is what we're going to use today, and you're going to use mostly over the next few weeks, although you'll have to go into the activity portal to use the telescopes, and we're going to do a little bit of that today. Let's see, I think if I click on the Educator Portal, I have to log in. And we are going to give you all a username that will probably be your first initial last name, and a temporary password that then you will reset. Students, we will be working with you once it's time to start implementing programs. We'll be working with you on a system for you to send us a spreadsheet of student usernames that are not identifiable, so that we'll never have students' names or any personally identifiable information of them. So I've logged in, and now I'm in this Educator Portal here, and you see this is all the material you need for the next few weeks. You have a checklist, and you'll be able to explore it. You see that the first thing on your checklist is take the pre-workshop survey, and you'll all be able to just check that off because you've already done it. And so this is to help you kind of keep track of the things you've explored. The second thing that we'll be asking you to do, or really as soon as you log on, tomorrow or over the weekend or next week, is to introduce yourself in our forum, another activity structure within the online portals. We have a number of forums in which we can conduct online discussions. And so the Introduce Yourself forum, Erica has started off by saying, please take a moment to introduce yourself to the rest of the community, and tell the group where you do, what you do there, if you have any experience in astrophotography, and what you find exciting about space. So I'm gonna actually make a post right now to show you how to do that. So I'm gonna reply to Erica, and an editing box opens up, and it allows you, actually sometimes it may open up with just this formatting tool, and this upper left tool, if you click on it, opens up other things. So there's all kinds of things you can format your emails to be lovely. So, but I'm just gonna, I am Mary Dussault from the CFA. I love astrophotography, and I particularly like using robotic telescopes to do it because I am of an age that when I was studying astronomy in undergraduate, for my undergraduate work, I had to sit in a dome in the cold for an hour while keeping the telescope moving to point at the object and expose the film for an hour of time to get all that light before there were CCD detectors like there are on MicroObservatory. So the kinds of things you and your students will be doing today and over the next few months are really how astronomy is done today, and it's very exciting. So let's see, I'm also going to add a picture to my post, and some of the activities ask you to post a picture possibly that you've created using the telescope, but I'll just show you how to do that. I just clicked on this little button up here. It looks like a little mountain. And this allows you to upload an image from your own computer. If you click on upload, it's fairly self-explanatory. You can choose a file, and it will open a box here. Okay, and I'm going to put in a little lagoon nebula here, and I'll name it. And upload it. So here's my image. It asks for an image description, and that is for people who have screen readers. It's a good idea. It's an alt tag. When you hover over the image, it describes it. So I'll just caption the image. And then over in appearance, there's another, I can just insert that and upload and it'll appear, but it's a little bit big. I want to shrink it so it has dimensions. I'm gonna, instead of 650 pixels, I'm gonna make it 325. And insert. There, so now I have a nice picture in my post. I'll post to the forum. And there it is. So I've replied to Erica, and now, and I'm hoping all of you reply as well. When you go back, you can see that my introduce yourself automatically checked itself. So some activities automatically check themselves, and some you manually say, yes, I've done this. And that's the same for the youth as well. Okay, so let's go take an image using the telescopes, and I'll show you how to do it through the YouthAstroNet portal. For that, we have to go back to the activity portal. And this, in the upper left of your screen, there's always a little breadcrumb trail of how the site is organized. So we're in the educator section. You want to go back to the main section and into the activity portal. And so now you can see we're in the activity portal. And this is where your students will do all their work. And this top section has some general information that will be useful and forums, but the bottom is where all the activities are. And when I mentioned at the beginning that Aladdin wasn't at this webinar because he's dealing with some little glitches, one is that all our pictures are not showing up. This upper left box that says MicroObservatory tools is one you'll be using all the time. So when I click on that, you'll see there's basically 3 functions. One is the telescope image request. That's how you send a request to our network of telescopes about what you want to take a picture of and how you want it to take that picture. There's a list, an image list, get the images you requested. Right within your account, you'll have access to images as they come back from the telescope. And it will keep images for the last month. And then this third function is to actually work with the images. And we're going to do all 3 right now. So first, you can request an image. And you can see that we have targets in the solar system, targets that are stars and nebula that are outside of our solar system, but inside our galaxy. And then targets that are other galaxies beyond our galaxy. And it turns out that this organization of the universe, that there's our star, the sun, and all our planets going around it, and then all the other stars you see in the sky are part of the Milky Way galaxy, which is much bigger than the solar system. And then beyond the Milky Way galaxy, there are billions of more of other galaxies. And that structure is often something that people who haven't been taken a lot of astronomy, or just kids who just were involved in their grade school astronomy, you learn all about the solar system, but you don't learn about that structure. There's information in your, there's also some information about each of these targets in a resource section. Okay, so let's see if we can have a few suggestions for objects anybody would like me to take here. You can type them in the chat box. This is where I find out if folks are out there listening. So anybody, you see this list of objects? Is there anything anybody wants me to observe?
We got a crab nebula.
We got a crab nebula. Oh, I see. I'm not. Oh, I got a bunch of them. Okay, there we are. Ring nebula, ring nebula. Okay, crab nebula. Let's go for that crab nebula. Where'd it go? Ah, there it is. All right. So this interface, some of you may have previously used our public interface, which is available at microobservatory.org, and it looks just like this. But the nice thing about embedding it in your YouthAstroNet account is that all your images get managed and land in your account and get saved there online. To get the telescope to take an image of an object in space, you're going to specify 3 parameters. One is the field of view of the telescope. And field of view is, I just put it down here. Here's an example of what you're doing when you choose field of view. Our telescopes, the best setting for most objects is the main camera of the telescope, which takes a picture that's a 1 degree field of view. And what does that mean? That means if you reached your pinky out and tried to cover the sky with your pinky fingernail, if you imagine a string going from your eyeball to the top and bottom of your pinky fingernail, that angle would be 1 degree, that angle. And so if you went pinky over pinky 90 times, you'd get to 90, you'd be right overhead. So the telescope looks at a patch of the sky that's just 1 pinky fingernail patch of sky. The zoom setting looks at half of that, so it zooms in to see only half of that. And the wide view setting is a patch of sky the size of your fist. So field of view is an important idea in astronomy, and as you explore images taken at those different settings, you'll start to notice some different things. But let's go back to our interface. Whoops, wrong interface. There we go. So we're going to, this crab nebula only offers the normal field of view. The moon and some other objects offer those other 2. And we have exposure time, and we have from 0.1 seconds to 60 seconds. And the exposure time is really telling the telescope how long to open up the shutter that is just above the detector. there's a little shutter, and here's a picture of one right from Frank's lab here, and you can see what it looks like when it's closed and when it's open. And the longer it stays open, the more photons of light coming from the universe fall into the telescope and get focused onto the CCD detector. So for the Crab Nebula, do we have any guesses, again in the chat box, of whether we want a long exposure or a short exposure for something like the Crab Nebula? And if you could type in the chat box short or long and why you think so. So Matt, why do you think long? I realize low light. Yeah, okay. So the Crab Nebula is a dim object. You can't see it with your naked eye. It's very dim, so you need to let a lot of light in. And 60 seconds, in fact, it's telling me the optimal exposure time. If I checked 1, I would get this note that it's underexposed. Then you have the ability to ask for different filters. The telescope has a filter wheel that when you set that setting in the portal, you're telling the telescope, okay, I don't need a filter. I want all the light I can get, so no filter. Or I want to limit, I want to just see what red light is coming from this object, or what green light, or what blue light. And so that's what that setting allows. At the next webinar, we'll be talking about more about light and color and filters. Right now, I just want to let you know that that is an option, and we'll be doing some activities with them. So for the Crab Nebula, I'll just choose multiple, because you can do one at a time, but or no filter, but let's choose multiple. When I hit continue, you see Crab Nebula was requested for MDUSALT. Click here. That request is now logged in my second function of the MicroObservatory tools, my list, my image list. Right here at the bottom, you can see that my request for Crab Nebula is pending, and I have lots of other requests pending. But I have some requests up here. These are all my requests that have come in from the telescope. So I'm going to go back to the main page, this link here. Get back to the robotic tools. Now, let's see, I think now we're going to go use the images. But first, I just want to show you, this is kind of what's going on with the telescope. It's a 6-inch aperture, or opening to the telescope is 6 inches. And the opening of the telescope is what astronomers are often very interested in, because the bigger telescopes let in a lot more light. And even though the CCD of the MicroObservatory telescopes is not as high resolution as the ones in your cell phone, for example, that big opening lets in a lot of light, a lot more than your pupil. And also, because you can expose over time, you can let light fall for 60 seconds, you can see much dimmer objects. But those telescopes are not in a dome. They are out in the open. So if it's cloudy tonight, you're going to get an images of clouds. And these two images, it was partly cloudy, so you got a little something, but sometimes it's possible for your image to be blank. And it turns out that the ability, well, we hope that the fact that we have a telescope in Arizona means that often you get good images back. But the ability to fail, the fact that this is real images coming back from a real telescope, turns out to be really important for student learning and ownership of the images that come back. So, all right, we've asked for the Crab Nebula. The telescope isn't going to go take that until tonight, but let's see how we use, let's see what we can do with an image that comes back, because I have some in the archives here. Let's see. So I go back to those robotic tools, and this is use the images in JS9. And JS9 is an image processing tool that's right in the browser. You don't have to download any extra software. It's right in your YouthAstroNet account. And some of you who may be familiar with using the downloadable software of MicroObservatory image, we are working to get all the functionality of that in this online browser. So I have in my list, all of you will have these archived images once you get your account, because we've put those in there as kind of demo images and things to work with until you have images of your own. And then you see my list. All the images that were in that green archive are also here to be opened. So I'm going to open the moon from actually back a couple weeks ago. Here it is. So it opens up in the tool. And as I move my cursor around the moon, you can see some things changing. You see this quantity changing and physical location. So if I wanted to find the place with the highest pixel value, can anyone describe in the chat box where I would go and where I should put my cursor if I want to get the highest pixel value in this image? Over here, anybody describe in the chat box as you look at this image, where should I put my cursor to get higher than 369? I want to get higher than 374. Where should I go? Where it is darker. If I go back here, I have 287. So that does, what if I want a high pixel value? So let's try where it's brightest, right? Follow the light. Yes, right. Good. So yeah, right. So that little spot there, that impact crater, is the brightest part in the image. It's 588. And so understanding that images are really just grids of, let's see if I can just find that. So the software basically takes a grid of numbers. That's the code that gets sent from the telescope back to your computer. And the software says, okay, I'm going to assign the high numbers white values and the low numbers black values, and the things in between levels of gray. So let's go back to our moon. Now, those pixel values, that what was the highest I got? 561 here, 580 in there, okay. I can make the image look brighter if I use these tools down at the bottom, high brightness limit and low brightness limit. So I'm going to slide this slider down. And now I've brightened up, I've made it look brighter, but notice the pixel values are still the same. That area in there, I can't even find it anymore. It's all overexposed. It's still, I don't know where it is. To go back. Where is it? Down in here. Okay, yes. still the same. The background is still in the 280s, even though I've brightened it all up. The background is still in the 280s. So image processing is all about displaying to enhance different features, but the data behind the visualization stays the same, those pixel values. So you can play around and try and bring out different features by changing these values. And let me show you a few of the other functions here. Let's see. I kind of like that because I can really see these craters in the bottom, but I want to see them better, so I can zoom. And zoom 1 is where we are now at zoom level 1. Zoom 2 means it becomes twice as big. And so I can start to see those craters. They're kind of off the screen. So there's a set of tools here. I'm going to use a magnifier. Oh I don't want a magnifier. I want a panner. A panner, so I can pan and see those craters that I wanted to see. I'm going to zoom in again. And as I keep zooming in, now they're starting to get very pixely, right? You can really see that this image is made of pixels, each of which have an individual value. In fact, there's a very cool tool called a pixel table. And when this is a great tool for teaching. So when I put that up, as I move my cursor, if I hold my cursor over a dark spot in the image, the background, you can see every pixel around my cursor is that low value of 287. If I put my cursor way over to this nice bright spot here, right? You can see that bright spot is 469, and things around it kind of fade off into 429s and things like that. So you're inspecting the data that's behind the image. So there's some fun tools. I'm going to go back to zoom level 1. But perhaps the most enjoyable tool is around colorizing the image. And what I'm going to show you today is how to false color an image. At webinar 2, in a week or so, on January 25th, 26th, we're going to talk about true color using the RGB filters to create an image of objects that is actually the color. If you could see if your eyes could gather enough light that you would see them in space. But today we're going to false color an image, and Frank's children have actually given these names to these various false color palettes. The scientists who developed the software had names like A and B and BB1A and AOB, and so his children decided that AB made it look like watermelon. So you can see now that there's a lot of flexibility. You can enhance different features as you adjust the settings to really enhance the image. And different colors, like the place I've put it in right now, really pulls out this ridge of craters. Whereas some color combinations look fun, but don't allow you to see as much. Like this starts to overexpose down here. So the false color is basically it's basically paint by number. It's taking these values and saying, okay, anything that's 419, 418, color it pink. Anything that's in the 200s, color it green. We have some hands-on activities that YouthAstroNet does that will help kids understand that. So they'll be coding different images for each other, and then another group tries to decode what the image is from the colors. So that's really the technology behind image processing that's used in many, many different careers and fields. Image processing is a key technology these days. Another tool that you'll want to know how to use is the region tool. You can create a box on your image, or I'll delete that. You can create a circle, or you can create a text region. And let me show you how the circle can be useful with a picture of the moon. If I want to figure out what's the diameter of this moon in pixels, if I try and get this circle right around it here, there, I've got my circle to fit the moon, and then I go to Analysis and say Region Stats. And this tells me that my circle is 350 in width and 350 pixels in height. So you can actually do measurements, and you can measure a little crater as well inside your moon and determine the size of that crater. If you know the actual diameter of the moon is 2,000 miles and it's represented by 350 pixels, then you can just use simple math to figure out what size all these craters are. So there's the M in STEM. Okay, I'm going to close my region here. Close, delete that. Okay. Now, if you want to post the image somewhere else in a forum, as the one I just did, what you'll need to do is actually let's put my name on it here. So I selected the text region. I double-clicked on the text region, and I'm just going to say Mary's Moon. Mary's Moon. Okay. And then I'm going to apply that text box. And then I'm going to make it big. And I'm going to make it diagonal. I'm going to put it like that. Yeah, I like that. All right. And now currently there's two ways to get this image onto your own computer. One is to hit the print button, and you see there it is, and so you can print it to a PDF. The other, of course, is to do a screenshot. We're trying this save as a PNG file should be the thing to use in the future. But right now, when you save as a PNG, as a PNG file, the text doesn't, you'll get the nice color image, but the Mary's Moon, the text doesn't come out. So the print is the best function to get that. All right, are there questions? At the moment, you've answered them. Okay, good. I'm glad. They're great. All right. Let me see. All right. So that's kind of a brief introduction. Your mission, should you decide to accept it over the next week, is that you yourself are going to take some images. You're going to use this tool to colorize them and make them look the way you like, to bring out different features. And then you're going to post your image onto the discussion forum. And I want to go back and show you those. But before we leave the image processing,
That's a question.
oh, there's another question.
Let's get into a thumb drive.
You absolutely can save onto a thumb drive. Yes. Yes. Yep. Thank God. Yeah. No. Oh, that's the recording. Okay. So the images are digital, and I have a little challenge here for you to see how well you have understood this idea of brighter pixel values mean lighter higher brightness value. Wait, did I say that right? Higher pixel values are had more photons. Here's an image that came into a detector. And remember, this setting takes all the things that are numbered 1 and colors them dark, takes the things that are numbered 8 and colors them white, and all the things that are 4 are levels of, are kind of medium gray, and 6 is a little bright gray. So can anyone predict what this is an image of? If 8 is white, 6 is off-white, kind of light gray, and 4 is dark gray. Remember, 8 is white. This is I know, taxing your, so there's a white spot here, a white spot here, and a bunch of white spots like this.
There we go. We got an answer.
Ah, okay. So let's go to the, yes, okay, right. So there's a couple of activities about going from pixels to pictures, hands-on activities that help students understand that. I want to give you, and these tools that you're using are really the same exact tools that astronomers here use. In fact, JS9 is being developed by software developers here and is used by the professional astronomers. This is a raw image. This is that comes back from the Chandra X-ray Observatory satellite, NASA's X-ray telescope, and Joe DePasquale, who's one of our STEM mentors, who will be on the discussion forums, and students can, he will have opportunities to present webinars about how he does his image processing, and he uses the same tool. I want to give you some examples of investigations students can do. Moon phases, if they take an image of the moon every night, they can investigate the phases. They can make a moon calendar. On the left there, if you want to integrate history, art, and science, the left is actually from Galileo's notebook. Galileo was one of the first to train a telescope on the moon, and one of the first to realize that the moon was not a perfect sphere. It had craters and mountains, and you could see them with the telescope. You can also take images of Jupiter over time. Here's Galileo again, training his telescope, and that little round disk is the disk of Jupiter. But then he saw these 4, and he makes them as little stars, but these 4 little dots that kept moving. Here's a MicroObservatory image of Jupiter, and here we see 3 of the dots. Although we also see this weird spike. So this is, so given what we've talked about, can anyone enter a chat box theory about why and this image of Jupiter has this weird spike going through it. Any theories? I'll give a little wait time. Yeah. So in order to get the light from the Jupiter's moons, we had to have a long exposure for this Jupiter. And too many photons fell on a single pixel on one of those single squares, and the signal kind of bleeds to the pixels above and below. So when it's overexposed, that's why you get a stripe like that. So, but you can take pictures of Jupiter over several nights and track and see the 4 moons, which we now know look like this from NASA instrument space probes that have gone to these planets. You can also investigate the sun over time. Back in 1610, Galileo observed sunspots, and you can see them too. And you can actually see the sun rotate if you take images of the sun over several days. I will mention, however, that you won't always get an image of the sun back right away when you request it through the portal, and that's because the sun is the one image that actually requires a human in the loop. Frank goes up on the roof, but only if it's sunny, and it is winter here in Cambridge, and he puts a special filter on the telescope in order to be able to take an image that doesn't destroy the CCD detector because there's so much light coming from the sun. A couple other features of the images that come back from the telescope. Unlike images in textbooks or on the web, the images from the main camera of MicroObservatory, now this is not true if you use the zoom camera or the wide field, but all the images from the main camera, since they're taken with the camera, they're at the same scale, and they really give you insight into the actual size of objects in space. So on this slide, on the left is a picture of the Hercules Nebula, and the Hercules star cluster, globular cluster. And if your eyes could see that in the sky, it's so dim that there's not enough light for your eyes. But it would be pretty big. It would be 1/3 of the size of the moon. So it's a big object on the sky. But there's a third object in this slide that you may have to do some searching around. Can anybody find the third object? I did a composite image on here. And there's a third image taken with the same cameras. I took the moon, and yes, Sandra, right, the lower right corner of the moon image here. You can see Saturn. So the first thing your students are going to want to take an image of is Saturn, and it's going to come back kind of like that. So it's the same. We know Saturn's a lot bigger than the moon, but of course it's so far away, it's a lot smaller than the moon. And so the MicroObservatory telescopes are actually great for deep sky images, which are actually big on the sky, and great for the moon and sun, which are big on the sky. But the Saturn, you have to use the zoom feature once you get it into your JS9, and then you'll just see pixels. So, but here's a a range of objects, and you can see that some of these objects are, you know, the Andromeda galaxy is bigger on the sky than the full moon, but it's very dim, so you have to be in dark skies to see it. There's a lot of size and scale activities you can do using these. I realize we're running to the end of our webinar at the moment, so one activity is to assess how well people understand this difference between solar system, things in our galaxy, and things beyond the galaxy by putting these objects in order from nearest to farthest or from smallest to biggest. And so those are some activities you can do. For example, in this slide, you know, we know that Jupiter is bigger than the moon, but again, it's farther away. So in MicroObservatory, it's smaller. And we know that the moon is a lot smaller than the sun, but it's a lot closer. So the sun is a lot farther away. And in fact, the happy coincidence that gives us eclipses is that the moon is about 400 times smaller than the sun, but the sun is 400 times farther away. And those two 400s cancel out, so they look exactly the same size in the sky. All right. I want to kind of remind you that the kind of the essential parts of what YouthAstroNet programs are is to learn to use the telescopes, to create something, to pursue a project using the telescopes, could be a movie, and in fact, if we go to the portal, back to your portal here, Educator Portal, Erica has loaded some examples of capstone projects from students who have done, who have used the telescopes and done activities like these. You can see these students from the Cerritos Library in California created an exhibit. Here's an example of creating images that show the difference between real and false color. We talked about that earlier. And there's some other examples that you can explore as well, and we'll talk more over the time that we're online. All right, so your mission now. Next steps. Erica's going to send you a username and password, but only if you've sent her a Gmail account address. So by the next webinar, we want you to go through that checklist, introduce yourself to everyone else, request an image, process that image with the online tool, see if you can figure out how to download and then upload your image in a forum. And I think you're going to create a tutorial, a video tutorial for how to do that is actually will be right on the portal. And keep the questions coming, keep the discussion going. We'll be online, looking forward to talking to you. That's your mission. Right now I'm going to stop and ask if there are any questions. Oh, Erica wanted me to remind you, okay. Next week, we do have, if you're on the portal, you see these upcoming events. We've scheduled some live office hours where we will be on the Zoom here. And if you have a burning question or you can't figure something out and you don't know how to write the question, you can just click on the Zoom link and we'll be here to answer your questions. And the times for those office hours, there's a half hour on Tuesday, a half hour, there's actually, I think we have two half hours on each day next week. So we'll kind of be monitoring those. Thanks. Questions? Yes, if you have other teachers,
I've never responded.
you have, okay. Yeah, if Erica has been communicating with people who have extra teachers. There's a little bit of some logistics involved with those of you who have other teachers you want to bring on board, and she'll communicate with you directly about that. All right, looks like you're all raring to go and dying to get that username and password. So I just want to say again that we're really excited to be starting this new project with you guys. Are Cohort A, having all you try out these new tools using MicroObservatory and engage your youth. And we hope to learn as much from you over the next few months as we hope you'll learn from us. So we'll see you on the portal.
We always got style.
Yeah. All right. Good. Well, thank you all so much. I'm going to see if I can figure out how to end this meeting, but you're welcome to, if you can figure out how to leave it, you can do that. Let's see. Oh, I'm going to stop.